Hello students, welcome to EPG Pathshala. I am Professor Panchapakeshan from University of Delhi. Today we are going to discuss about the module Dirac Equation for Electron. This is from the paper Radiation Theory in the course on physics. After studying this module, you should be able to understand how Dirac looked for a linear relativistic equation of motion and had to bring in spinor fields and matrices now called Dirac matrices. You also learned about the Dirac equation for the electron. Learned how the Dirac equation of electron is Lorentz covariant. Learned how the intrinsic spin of electron follows naturally from the extra components and the spinor nature. Learn about plane wave solutions for electron field and how they can carry positive and negative energies. We have quantized the classical electromagnetic field and studied various processes like absorption, emission, and scattering of particles. The classical particles were, however, treated non-relativistically. As the energies of particles increase, we have to treat the classical particles, which are always fermions, relativistically. This requires us to consider an electron obeying the relativistic equation, now called the Dirac equation. Klein-Gordon equation was the first relativistic equation to be quantized. However, it met with difficulties of negative probabilities and negative energies. Klein-Gordon equation starts with a squared Hamiltonian. Dirac thought that this created the problems of negative energies. He started by linearizing the Hamiltonian. This meant taking a first-order time derivative instead of the second-order time derivative. Schrödinger equation uses a first-order time derivative. This, however, forced Dirac to go to the spinor wave function and the 4x4 Dirac matrices. In spite of these complications, the negative energy problem was not overcome. The quantization, however, leads to a field theory with a many-particle interpretation. Dirac, who found that the Pauli principle for the electrons requires the imposition of anti-commutation relations and not commutation relations for quantization. Earlier, we were using the commutation relations for quantizations, but in this module, we will find we require the anti-commutation relations for the electron field. The many-particle interpretation enabled Dirac to avoid the negative energy states by demanding that they be all filled up in a normal ground state or vacuum. When one of them is knocked out, we have a hole or a positron, which is an antiparticle of the electron. This uncomfortable result turned out to be a successful prediction when positrons were discovered in 1932 by Carl Anderson. We start by linearizing the Hamiltonian in section 3 and study the spinor wave function and the accompanying gamma matrices and their properties in section 4. In section 5, we introduce the Dirac equation and study its relativistic covariance. In quantizing the Klein-Gordon field, we had difficulties with the energy of the particle. As the expression has square of energy, it gets represented by a second-order time derivative. Energy has both positive and negative energy square root values, which also create problems. Dirac thought it may be better to work with a linearized Hamiltonian which is linear in the time derivative, like the Schrödinger equation is. So, starting with h squared, which is the operator for energy squared, is equal to p squared plus m squared, Dirac took the linear form Hamiltonian is equal to gamma naught into gamma dot p vector plus m. With gamma dot p is a product, three vector product of gamma and p. It can also be written as gamma I pi, the usual three vector scalar product. As h and p are Hermitian operators, the Hamiltonian and momentum are Hermitian operators, gamma naught gamma and gamma naught are Hermitian but constant matrices. However, as we will see later, gamma I by itself need not be Hermitian. Squaring 3.2, namely the Hamiltonian, we get the Hamiltonian squared is equal to half into gamma naught gamma I into commuted with gamma naught gamma j into pi pj plus anticommutator of gamma naught gamma I and gamma naught and pi m plus gamma naught squared m squared. Brackets are all anticommutators here, and we denote them with a plus sign to denote the anticommutators, and the anticommutator of a and b is ab plus ba, which is also of course equal to anticommutator of b with a. Comparing with equation 3.1, we find the three equalities, namely anticommutator of gamma naught gamma I with gamma naught gamma j is equal to twice delta ij, anticommutator of gamma naught gamma I with gamma naught is 0, and gamma naught squared is equal to 1. Simplifying these equations by using the last one in the second and the second one in the first, we get to the equation gamma I gamma naught plus gamma naught gamma I, or the anticommutator of gamma I and gamma naught, is equal to 0. Using this in the equation 3.5, we get minus times the anticommutator of gamma I and gamma j is equal to twice delta ij. As gamma naught anticommutator is 2 and gamma I gamma naught anticommutator is 0, all these equations can be combined and written as anticommutator of gamma nu is equal to twice g mu nu. An identity matrix is understood on the right hand side. Dirac noticed that to satisfy equation 3.9, gamma mu should be at least of the order 4 into 4 matrices or larger. The gamma matrices and their properties. Tracelessness. The matrices are traceless for all of them. Trace of gamma mu is equal to 0. For example, take gamma squared. Trace of gamma squared is minus trace of gamma 2 gamma 1 into gamma 1, as gamma 1 squared is equal to minus 1. We have added this gamma 1 squared and change the minus sign to minus sign, which is equal to trace of gamma 1 gamma 2 gamma 1, as gamma 1 and gamma 2 anticommute. Using cyclic property, that is trace of ABC is equal to trace of CAB, this leads us to trace of gamma squared is equal to minus trace of gamma squared. So trace of gamma squared has to be 0. The spin angular momentum matrix is defined as sigma mu nu, which is I by 2 anticommutator of gamma nu, and which is equal to minus sigma nu mu. When you interchange mu and nu, it changes sign as it is antisymmetric. And because of the antisymmetric property, there are n into n minus 1 or 6 of these independent matrices in 4 dimensions. They are related to spin angular momentum of fields obeying Dirac equation or particles of half integral spin. We also define a gamma phi matrix, which is the product of all the 4 matrices with an I. It is I gamma naught, gamma 1, gamma 2, gamma 3. It can also be related to another matrix called the anti-symmetric tensor, another tensor called the anti-symmetric tensor, I by 4 epsilon mu nu lambda rho, gamma mu, gamma nu, gamma lambda, gamma rho. The interchange of any two indices introduce a factor minus 1. So epsilon mu nu lambda rho has only one independent component, which is usually normalized to 1. We use the convention epsilon 0, 1, 2, 3 is equal to plus 1. For gamma phi, there is no distinction between upper and lower indices. Using gamma phi and sigma mu nu, we can construct 16 linearly independent matrices. Gamma mu, we write it as capital gamma mu, which can have the value 1 or gamma mu or sigma mu nu or gamma phi gamma mu. These are respectively called the gamma scalar, gamma vector, gamma tensor, gamma pseudoscalar, and gamma axial vector. These can be thought of as spanning a 16-dimensional space of matrices. Therefore, the matrices must be at least 4 into 4. Anti-Hermitian gamma I. As gamma naught and gamma naught I are Hermitian, gamma I dagger is equal to gamma I into gamma naught squared dagger. We put the gamma naught squared because gamma naught squared is equal to 1, and if we take the dagger, it is gamma naught dagger into gamma I gamma naught, which is equal to gamma I gamma naught, which again becomes equal to minus gamma I. So gamma I is anti-Hermitian. Including gamma naught, we can write the gamma mu dagger as gamma naught gamma mu gamma naught. Uniqueness. If U is unitary matrix, for any set of gamma mu, another set gamma mu tilde defined by gamma mu tilde is equal to U gamma mu U dagger will also satisfy equation 3.9 and 3.16. So the set of gamma mu is not unique. Of course, if gammas change, other quantities in the physical quantities will also change correspondingly. Dirac equation and Lorentz covariance. Dirac equation, if you put Hamiltonian equal to I d dt and take momentum vector as minus I delta in the equation 3.2, we can write the equation of motion of the wave function psi as I d dt psi x is equal to gamma naught minus I gamma delta plus m into psi vector. This is the Dirac equation. Multiplying from the left by gamma naught, we can write it as I gamma mu d mu minus m operating on psi x is equal to 0. Defining the slash notation for any vector a mu as a slash is defined as gamma mu a mu with mu upstairs and mu downstairs, or mu downstairs and mu upstairs, where gamma mu is equal to g mu nu with mu nu below, gamma nu on top. We can write the Dirac equation as I d slash minus m operating on psi x is equal to 0. Dirac's equation is usually written in the form of 4.2 or 4.4. As gamma mu are 4 into 4 matrices, psi x must be a column matrix with 4 entries. As gamma mu are not unique, psi x will also not be unique. For a change of the basis gamma mu with energy matrix, with unitary matrix U, phi x will change as psi tilde is equal to U operating on psi x. Relativistic covariance. The requirement that Dirac equation be relativistically covariant fixes the Lorentz transformation property of psi x if x mu goes to x prime mu, which is equal to a mu nu x nu, the usual Lorentz transformation, then Dirac equation becomes I gamma mu d mu prime minus m psi dagger x prime is equal to 0. The transformed wave function is taken to be linearly related to the original wave function. So psi prime x prime is equal to SA into psi. Using equation 4.8 and 4.7 and using the transformation property d mu prime is equal to a nu mu d nu, we get the equation I gamma mu a mu nu d nu SA psi x minus m SA psi x is equal to 0. Multiplying this equation on the left by S inverse, we find that S inverse I gamma mu a mu nu d nu S psi x minus m S inverse S psi x is equal to 0, where we have not shown the dependence of S on A. Comparing the equation 4.2, we get the equation S inverse gamma mu A nu mu S is equal to gamma nu, equation 4.12. Multiplying by A rho nu, rho above and nu below, and using A rho above and nu below into A mu below and nu above is equal to g rho mu, which is equal to delta rho mu. This can be also written as S inverse gamma rho S is equal to A rho nu gamma nu. So this is the equation which helps us to determine S and provide the Lorentz covariance. To do this, we consider the infinitesimal Lorentz transformation. We consider an infinitesimal Lorentz transformation A mu nu is equal to G mu nu plus omega mu nu, where omega mu nu is equal to minus omega nu mu, or it is anti-symmetric. This is to make sure that the product of A's or G's will reduce to 1. We want SA to be linear in omega mu nu and reduce to identity as omega mu nu goes to 0. So we take SA equal to 1 minus I by 4 beta mu nu omega mu nu, and correspondingly S inverse is 1 plus I by 4 beta mu nu omega mu nu. And using this, we find that 1 plus I by 4 beta lambda rho omega lambda rho into gamma mu into G nu mu, nu on top, mu below, omega nu mu, nu on top, mu below, into 1 minus I by 4 beta sigma tau below, omega sigma tau above is equal to gamma nu. If we now compare terms on both sides order by order, then we get the first equation gamma mu into G nu above and mu below is equal to gamma nu, which is just acting like the raising or lowering operator even with gamma. And if we then solve this equation, taking the terms with omega lambda rho on one side and remembering that omega lambda rho is an antisymmetric quantity, we reach equation 4.8, which gives us the commutator of gamma mu with beta lambda rho is equal to twice I G mu lambda below, gamma rho below, minus G mu rho below, and gamma lambda. This is the condition for the matrices beta lambda rho to satisfy so that the Lorentz covariance is observed. It can be checked that if we take beta lambda rho is equal to sigma lambda rho, which is equal to I by 2 commutator of gamma lambda with gamma rho, which is related to the spin angular momentum, then the condition 4.18 is satisfied. For finite Lorentz transformation, we can exponentiate the infinitesimal one in equation 4.13. The wave function transforms as psi prime x prime is equal to S as a function of A into psi x, which is equal to exponential of minus I by 4 sigma mu nu omega mu nu operating on psi x. Psi x, whose components mix among themselves, are called spinors and are in addition to scalars, vectors, and tensors studied earlier. Spinors satisfy equation 4.9 and need not be solutions of Dirac equation. Intrinsic spin of electron. The transformation equation 4.19, when combined with the angular momentum operator dealt with in the module on Noether's theorem, gives us psi prime x is equal to 1 minus I by 2 j mu nu omega mu nu operating on psi x. Combining equation 419 and 420, we find the total j mu nu is equal to I times x mu d nu minus x nu d mu plus half sigma mu nu. The second term shows that the solution of Dirac's equation carries an intrinsic angular momentum or spin. Thus, the spin of electron is a prediction of Dirac equation and is already built into the formalism of spinors, which provides the extra degree of freedom. Relation between S and its inverse S inverse. Lorentz transformation include change of coordinate system by space rotations as well as by change to another coordinate system moving with constant velocity. These are parameterized by rotation angle or the velocity, and this parameter varies continuously. These are called proper transformations, and determinant of A nu mu in equation 4.9 has determinant of A modulus is plus 1. Value of the determinant is plus 1. Space reflection or parity and time reversal have a determinant of A whose value is minus 1. They are called improper transformations. Equation 4.8 defines the function S which takes psi x to psi prime x prime. It is given by equation 4.18. For rotations, sigma ij in SR, where R refers to the rotation, are Hermitian, and SR dagger is equal to SR inverse, is the inverse. However, for the transformations to a moving frame, we can call it a Lorentz transformation or a boost, SL, then sigma 0I is not Hermitian. And SL dagger is equal to SL, which is not equal to SL inverse. However, it can be shown that S inverse is still equal to gamma naught into S dagger into gamma naught, or equivalently, S dagger is equal to gamma naught S inverse gamma naught, holds for both SR and SL. Bilinear covariance. We considered next the Lorentz transformation properties of the bilinear forms psi bar gamma mu psi constructed from the 16 linearly independent gamma mu, given in equation 3.14. One finds the Dirac conjugate psi bar, which is defined as psi dagger into gamma naught, is very useful for spinors. We notice that gamma mu gamma phi commutator is equal to gamma mu gamma phi plus gamma phi gamma mu, and so gamma phi sigma mu nu anticommutator is equal to 0, or S gamma phi anticommutator is equal to 0 for all proper Lorentz transformations. If we start with the scalar psi bar x psi x on transformation, psi bar prime x prime into psi prime x prime is equal to psi bar prime gamma naught psi prime, which is equal to psi bar S dagger gamma naught S psi x, which is equal to psi dagger x gamma naught S inverse S psi, which is equal to psi bar psi, which is a scalar. Similarly, we find the other equations, the one with gamma phi ends up as same, psi bar x gamma phi psi x. Similarly, using the equations, we find psi bar gamma mu psi prime goes to A nu mu psi bar gamma mu psi, and psi bar prime gamma phi gamma nu psi prime x, the axial vector, goes to determinant of A times A nu mu into psi bar gamma phi gamma mu psi. This is called a pseudo vector. And psi prime sigma mu nu psi prime, psi bar prime sigma mu nu psi prime is equal to A mu alpha A nu beta into psi bar into sigma alpha beta into psi x. This is a second rank anti-symmetric tensor. Plane wave solutions. Positive and negative energies and spin up and down. If we consider the single particle solution of Dirac equation, the problem of negative energy still persists. Consider a plane wave solution of the Dirac equation. The time dependence is of the form exponential minus I into Et. From the Dirac equation 4.2, we see that in the rest frame of the particle, where p vector is equal to 0, the eigenvalues are given by the equation gamma naught into energy minus m operating on psi x is equal to 0. As gamma naught squared is 1, eigenvalues of gamma naught are plus 1 and minus 1. So E is equal to plus m or minus m. So as Ix has 4 components, there will be 4 solutions, and eigenvalues and each sign of energy will have 2 independent eigenvalues which are connected to the 2 spin eigenvalues, giving 4 in all. So the negative energy difficulty has not gone away in the single particle interpretation of the Dirac equation. For the case of the finite momentum p vector, the general solutions can be written as psi x is USP into exponential minus IPX and VSP exponential plus IPX, where S takes the values 1 or 2 or plus or minus for the 2 independent solutions related to spin. USP is the spinor for positive energy solutions with E equal to plus square root of p squared plus m squared with momentum plus p vector. VSP is the spinor for negative energy solution with E equal to minus square root of p squared plus m squared with momentum minus p. The spinor satisfies the equation p slash minus m operating on US, which is a function of p equal to 0, and p slash plus m operating on VSP vector is equal to 0. Taking Hermitian conjugative equation 5.4a and using equation 3.16, we can solve for US and VS, and we find that UR dagger USP is equal to VR dagger into VS, which is equal to twice EP into delta RS, and VR dagger P US of minus P equal to UR dagger P into VS of minus P equal to 0 are the two equations which help us to fix the normalization of spinor by using these conditions, namely the conditions that US bar into gamma mu P mu minus M is equal to US bar P prime slash minus M. So the Hermitian conjugative equation 5.4a is US bar into P prime minus M is equal to 0. Similarly, we have the equation for Vs, which is Vs bar into P prime plus M is equal to 0. The solution of Dirac equation using the Dirac-Pauli representation. The Dirac-Pauli representation is gamma naught is equal to 1, 0, 0 minus 1. Gamma I is equal to 0, sigma I minus sigma I 0, where each term is a 2 by 2 matrix. I is a 2 by 2 unit matrix, and sigma I or 2 by 2 Pauli matrices given by sigma 1 is 0, 1, 1, 0, sigma 2 is 0 minus I 0, sigma 3 is 1, 0, 0 minus 1. Using these equations, we can simplify the equations, and if we use US equal to phi plus, phi minus, where phi plus are the top two and phi minus are the bottom two components, then we can separate phi plus and phi minus and solve one in terms of the other. And when we do this, we find the solutions of U spinors can be written as U plus minus P is equal to square root of EP plus M, and within operating on a matrix omega plus minus and sigma dot P over EP plus M into omega plus minus. And for V plus minus P is equal to plus or minus EP by plus M, and the matrix is sigma dot P over EP plus M into omega minus plus, and the bottom term is omega minus plus. The outside factor is due to the normalization factors which we got earlier. Negative energies. The presence of negative energy poses difficulties in classical theory. The energies vary continuously. One can assume that no electron with positive energy will have energies varying between 0 and high values. In quantum mechanics, the electron energy need not vary continuously. It can make a transition to a lower energy which can be negative. So the positive energy electron is not stable and will end up with high negative energy. Dirac solved this problem by using the Pauli exclusion principle. He assumed that in ground state of the electron system, which is the physical vacuum, all negative energy states are occupied, and so a free electron cannot make a transition to a negative energy state. This, however, leads to the possibility of a hole or a vacancy being created in the vacuum or the ground state by an electron going from the lower negative energy to higher positive energy. This creates a particle and a hole. The hole has an opposite positive charge. This explanation became a very striking prediction when positrons were discovered by Anderson 2 years later. This also led to a completely new and revolutionary way of thinking about the vacuum and particle-antiparticle pair creation from the vacuum. When we quantize the Dirac equation in the next module, we go to the many particle interpretation, and the negative energy states are assumed to be filled up, and their absence produces a hole or what is interpreted as a positron. So students, let us summarize what we have learnt in this module. We have seen how Dirac looked for a linear relativistic equation of motion and had to bring in spinor fields and 4×4 matrices, now called the Dirac matrices. We have learnt the Dirac equation for the electron and how to write it in a compact covariant form. We have seen how the Dirac equation is Lorentz covariant, and derived the transformation of other physical quantities under a Lorentz transformation. We have seen how the intrinsic spin of electron follows naturally from the extra components and the spinor nature. We have obtained the plane wave solutions for electron field and seen how they correspond to positive and negative energies, besides describing the spin degree of freedom. Thank you.